Welcome to part 4 of the nuclear physics videos. In this video we're going to take a deeper dive into alpha decay. If you haven't watched the videos leading up to this, you want to check those out because that will help this make a lot more sense. So what we're going to do here, as we saw in the last video, we're going to look at how we would write the nuclear reaction that shows the alpha decay. So I have element X here that has atomic mass A and atomic number Z. And that is going to naturally decay down into some new element X with atomic mass A minus 4 and atomic number Z minus 2. And we know that these are the two values because we can study the samples and see that consistently this is the kind of decay that occurs with alpha decay, meaning through the conservation of matter, and here specifically conservation of nucleons. In other words, we can't just delete nucleons. They have to be accounted for, and they are accounted for. They are the actual alpha particle, which has this 4-2 nature. Mass of 4, atomic number of 2. Now if you look at your periodic table, the element that has this 4-2 description is actually helium. So an alpha particle turns out to be essentially a helium nucleus. And the helium nucleus is fairly stable, so when you get some big unruly radioactive element, it slops off into pieces that are in the form of helium nuclei. Now let's do an example problem here so we can see some in actual play. Let's take uranium, and I'm going to take uranium-238. Now uranium-238 is an isotope of uranium because uranium's atomic number is 92. So we can see that there are an excess of neutrons here. And that's going to break down into something that's going to have the atomic number, or I'm sorry, the atomic mass 234, and it's going to have this atomic number of 90. It's of course going to have the helium nucleus, or the alpha particle. And so if we look on our periodic table, we see that element 90 is in fact thorium. And so we can see here that this sample is going to break down into thorium. Now, in addition to this, we can look at the amount of energy that's being released in this kind of reaction. And we're going to do it through the mass defect idea that we looked at in a few videos ago. What I'm going to do is switch our starting element. Let's switch it to plutonium. Now plutonium has a mass number of 239 in this case. It's an isotope of plutonium, and plutonium's atomic number is 94. Now when the plutonium breaks down through alpha decay, we know for sure that we've got this 4-2 helium. And so what I'm going to do here is do 239 minus 4, which will give me 235, and 94 minus 2, which will give me 92. And when I look back, I see that element 92 is uniquely uranium. So I have a uranium-235 that might break down as well. So I have this uranium-235 here and this helium nucleus, or an alpha particle. And what I'm going to do now is figure out the amount of energy that is emitted in this alpha decay. So we're going to use the equation again, E equals delta M C squared. And first we must find the mass difference, the mass defect, between the parent nucleus and the products of the decay. And the difference in those will give us the amount of energy. So what I'm going to say here is that the mass of the plutonium, this mass number is 239, specifically 239.052157 atomic units. And so that value is known. And now I'm going to find the mass addition of these two. So I'm going to say that I have 235, and there's some change here, that's atomic units, plus 4.002602, and this is going to give me the combined amount of 239.046526 U. Now we can see that if we find the mass difference between the parent nucleus, which is the plutonium, and the uranium-235 and the alpha particle, so we can find that difference, okay, what we find is that the difference is equal to 0.000561 U. So it's very small, but it's definitely there and definitely significant. Now's the time we're going to make the conversion. So what we're going to say here is we need to know that one mass unit, or atomic unit, excuse me, is 931.5 mega electron volts over c squared. So when we put this into the equation here, what we're going to do is essentially a conversion to get to the energy. And we're going to say that that mass defect, 0.0005631, times this factor conversion, 931.5 mega electron volts over c squared, times c squared. We just plugged in this with its conversion over here. We're going to get 5.25 mega electron volts. The energy released in this alpha decay is in the mega electron volt range. So that's many times greater than chemical reaction energies. So when we look at nuclear reaction energies that are exothermic, we see that there is a large amount of energy that's being released. And keep in mind that this is just from one specific atom. So the trick to doing these problems is to always remember that if you start with some element and you know it's going to undergo alpha decay, you know for sure that you have a helium-4 over here on this side, so the results are just the matter of subtracting and then taking a look at the periodic table if need be. Now, AP Physics courses, you don't have to know the periodic table. They will give you a variety of different answers, and you just have to make sure that your nucleons balance in the equation. In the next video, we're going to take a look at beta decay and gamma decay.